Hi guys, welcome back. Let us start. Today we'll start with what is the meaning of homomorphic encryption, and then we'll start with some of the basic things. So to start with, suppose your encryption function, that is, let us say denoted by EK, from plain text to ciphertext space. Okay, and suppose plain text is having this operation, and then ciphertext, these are the group, you can say ciphertext is having this operation. Okay, then what do you mean by encryption? That is homomorphic encryption of say two element A and B. This is equal to encryption of A star B. This is the basic definition of homomorphic encryption. Okay, why it is called homomorphic? If you observe on the plain text, on the domain is your plain text space, I am multiplying two element or multiply or whatever operation it is, it may be addition or subtraction or anything. I am denoting by start, so I am putting it A star B, and what do you observe? The final value is encryption of A and encryption of B applied with the operation on C. That's why it is called homomorphic encryption. In the case of addition, it would be encryption of A plus B, it will be equal to encryption of A plus encryption of B. And in the case of multiplication, it would be encryption of A multiplied B, it will be encryption of A multiplied with encryption of B. As simple as that. Okay. So the first time after RSA, which was invented in 1978 by Ravish Samir and Edelman. After RSA, there was a paper in 1978 by Ravish Samir, Edelman, and Dertozaus after inventing RSA. In that paper, they introduced a term privacy homomorphism. Now we call it as fully homomorphism, fully homomorphic encryption. Okay. In that paper, they have showed that what is the homomorphism and how can we what are the application of this and so on. Okay, so we'll first see what is RSA. Actually, before going to that, let us see what are the different type of fully homomorphics. I'll just stop it somewhere here, and then let us first complete one part. Types of homomorphic encryption. Types of homomorphic encryption. Yeah, so basically there are three types of homomorphic encryption, and sometimes sometimes it is in four also. In some book you will find four different type, and in some book it is three different type. The first is, I'll just change the color. Yeah, partial homomorphic encryption. Partial, I'll write HE. First is partial homomorphic encryption. In partial homomorphic encryption, the evaluation of circuits circuit means you can consider it as a function consisting consisting only one type of gate, only one type of gate, or you can say operation. Example, addition or subtract or multiplication or multiplication. What do you mean by this? That means you can either perform addition over encrypted data or multiplication. You cannot perform both. Only one of the operation is performed, that is called partial homomorphic encryption. Example is RSA. We'll come back to this. What are the different partial homomorphic encryption are there? Then one of the example is RSA, and then Goldwasser Mikali, and then Palier, and then BGN, and so on. So we'll be coming all about all of them. We'll be introducing all of them. Okay, so this was the first one. One more guy, El Gamal, is also there here in between. After, yeah, I got right. Yeah, these are the 5 main partial homomorphic encryption schemes are there. Okay, so let us discuss them one by one. Or first, yeah, I'll just complete the definition. This is partial homomorphic encryption, and the second is somewhat homomorphic encryption. Somewhat homomorphic. In this, you can evaluate 2 type of gates. You can evaluate 2 types of gates, or operations, that is, you can say addition and multiplication both, but only for a subset of circuit. What do you mean by this? That means you can solve encryption over addition over multiplication, correct? But the problem is here, only given a set that you can perform only, say, addition of these, this or something, you can say a square plus 2a, something like that. Only you can perform only these type of people. It is limited actually. We can say you can perform a square plus 7, a plus 8, some limited set is given, and you can perform only up to that. This is called subset of circuits. You can after that, if you try to do, then the decryption will be failed and you won't able to get the correct result. So what is somewhat homomorphic encryption? Here you can evaluate on 2 type of gate, whereas in the case of partial homomorphic, you can evaluate only on 1 type of gate, and there was no restriction of this. But in this case, in somewhat homomorphic encryption, there is restriction that you can perform only subset of circuit, not dynamically fully any type of circuit. Okay, so in literature, after somewhat, some of the book says that fully homomorphic encryption, the next definition. In literature, again there is one more definition, you can say leveled homomorphic encryption, which is quite similar to your somewhat homomorphic encryption. I'll call it as leveled homomorphic encryption. Is similar to somewhat. I'll just write. And I put a star also. In some book you won't find this definition. Okay, yeah. Here also you can perform both the type of gates. Okay, of bounded depth. As I told you, it is quite similar to your somewhat. In somewhat, it was given that only some type of operations you can perform, and in this case, you can perform up to some depth. What do you mean by depth? That means you can say only 10 multiplications, or something related to degree. You can solve only degree 5. So any polynomial of degree 5 you can solve, but if you go ahead, then there will be a problem. So it is that's why I told you. Whereas in the case of somewhat, I have listed all the circuits, all the operations which I can do. Whereas I am just stating that only for degree 5 people I can solve, otherwise I cannot solve, something like that. So that's why it is called leveled homomorphic encryption. Again, this is you can solve both addition and multiplication. The condition is that here it is condition on depth. So you can see it is next step to somewhat and similar actually. Next is the fourth one is fully homomorphic encryption, which we call it as FHE. Fully homomorphic. What happens in fully homomorphic encryption? Again, all the type of gate. You can see any circuit you can solve. Multiple type of gate. Or you can just say addition and multiplication, because you can solve any circuit by just using addition and multiplication. You can solve division, you can solve subtraction, and anything, just if you have this operation addition and multiplication. Multiple type of gate of unbounded depth. Whereas in the case of leveled, it was said that it can solve only bounded depth. Here in the case of FHE, you can solve any unbounded. That means here over the encrypted data, you can solve any of the circuit. There is no bound. You can solve any of the circuit if you are on the encrypted data. So this is very strong, and it has a wide application in the field of cryptography. Okay, so let us see how the journey of FHE begins. We'll start with RSA. I'll just stating the year also here. Let us see the history of in 1978, the first after as I told you. Yeah, so what is RSA first? Let us see. What is the key generation and what are the encryption decryption? Then we will see evolution. One more part is evolution here. That is homomorphic property, you can say. Here we are checking. So in RSA, actually it is based on factoring to problem. So let me say factoring problem. What is the first key generation? Key generation, choose two large prime P and Q. Choose two large prime P and Q and find N, which is P into Q. Okay, and you must be aware that it is easy to know N if you have the idea of P and Q. You can go from here to here. But if you are given N equal to something, then you cannot get the value of P and Q. This is called integer factorization problem, and this is hard problem. Yeah. Okay. So this is your, what is your public key? First choose two large prime P and Q, then n equal to P and Q, and what next? After that, choose the encryption key E such that E into D equal to 1 modulo phi of P, phi of n actually. That means E has inverse. And what is the encryption? Your public key is n, and your public key is E. This is encryption key, and your secret key is P and Q. N is also known publicly. Okay. So suppose I am having a message M, the encryption C will be M raised to E modulo n. This is the encryption. This is the ciphertext. What is the decryption? In the case of decryption, you just find out C raised to D modulo n. Now since you know that E into D equal to 1 modulo phi of n, you can get it as M, your message modulo n. Okay, as simple as that. Now let us see which homomorphic property it satisfies. And I told you that. Now let us see, I am having two messages, say M1 and M2. Okay, and I'll find out the encryption of it. What is the encryption? Say C1 equal to, this is M1 raised to E and modulo n, and what is your C2? It is M2 raised to E modulo n. This is two things what I am having. Let us try to see addition, whether something happens or not. C1 plus C2. What I am getting, M1 raised to E plus M2 raised to E modulo n. Does this give you something? Is this equal to some, say, M k something raised to E modulo n? No, because it is the addition, so I cannot do anything. I don't know whether the addition will be, so this need not be true. So this is false. Need not be true. And what about multiplication? Now check. Let us say, suppose C1 into C2 I am finding, then it will be M1 raised to E multiplied with M2 raised to E modulo n. Correct? What do you observe? Yes. Can I write it as M1 into M2 raised to E modulo n? What do you observe? In the case of multiplication, it is actually encryption of M1 into M2. Yes or no? It is encryption of M1 into M2. That's what I found out. That means this is homomorphic with respect to multiplication. It means only one type of gate I am able to solve. Addition I was not able to solve. I am able to solve multiplication. So this is which one? Partial homomorphic encryption. This is the example of partial homomorphic encryption, because I am able to solve one of the gate, that is multiplication here. Correct? Okay. Then what next? This happened in 1978. Then in 1982. 1982 there was a crypto system, that is Gold Washer. Gold Washer Mikali encryption scheme. Okay, this was given in 1978, and this is first probabilistic public key system. First probabilistic PKC. Okay, and even if you will be amazed to know that Goldwasser Mikali is the one who has given the definition of symmetric security. Proposed definition of semantic security. Okay, now let us see. Uh, and the first thing is, on which problem does this Goldwasser Mikali crypto system lie on? Okay, so it lie on whether x is square modulo n or not. Square modulo n or not. Okay, this is the problem. Whether x is a square modulo n. That means what? There is some, say, y square equal to x modulo n. Does this y exist or not? This is the question. Okay. Now, given the factorization, say p and q of n, that means n equal to p into q. Suppose I know the factorization p and q, then this can be easily solved. What do you have to do? You just have to find xp, which is, say, x modulo p, and find xq, which is again x modulo q. The value of x, I will take mod p, I'll get xp. Again, I'll take mod q, I'll get xq. Okay, and if xp raised to p minus 1 by 2 equal to 1 modulo p, and xq raised to q minus 1 by 2 equal to 1 modulo p modulo q, then we say that x is quadratic residue modulo n. Then this will imply that x is quadratic residue modulo n. Okay, but if you don't know the factorization, then this is again a hard problem. Okay, so based on this crypto system was designed. If you know the factorization, you can easily get to know whether it is a quadratic residue or not. You just have to check whether it is quadratic over p and q. So best way to check this Lagrange theorem, Lagrange notation, to check whether it is quadratic residue or not. Okay, now let us see the crypto system. First is key generation. Key generation, again, I told you that we need only p and q here. In the case of key generation, I am having two large prime p and q. Okay, and your n is p into q. One more thing is here, p and q should be 3 modulo. This is Blum integer. This was the condition for that. And find a. Find a, which is non-residue. Non-residue. That means a, say ep, I'm saying p raised to p minus 1 by 2, it is equal to minus 1 mod p. That is, this is quadratic non-residue. Okay, and also aq. What is ap? It is a modulo p. And what is aq? It is a modulo q. So aq raised to q minus 1 by 2 is again minus 1 mod p. This is the definition of quadratic non-residue. Okay, so what is the public key? Your public key is e comma n. And what is the secret key? Your factorization. P comma q is the secret key. Okay, now let us see encryption. How do you encrypt? Okay, suppose We want to encrypt the message M. To encrypt a message M, first decode it in the bits. So first thing is I'll write M as a string of bits. Let me call it as M1, M2, MCN. So each MIs are a bit. Okay. Now what he's going to do for every bit MI, for every bit MI, okay, generate a random value BI. Generate a random value BI from the group of units of modulo n. From group of units modulo n. Okay, or you can just say that GCD of BI comma n should be 1, so that I can find the inverse of BI. Then he output what is the ciphertext CI. CI will be BI square and e raised to mi modulo n. That's it. Okay. So, and the ciphertext will be, what is the ciphertext? It will be C1, C2 and Cn. This is the encryption, as simple as that. I'll just repeat what I am doing. Suppose I would like to encrypt this message M. First write M in the bit form, M1, M2 up to Mn. Then for every bit Mi, generate random value Bi. This should be Bi. And then compute Ci equal to Bi square E Mi. Do you observe something? Suppose I am putting message M. I am getting some value of some ciphertext C. And if I am putting M, then I may get some ciphertext C dash. I may not get the same C, because every time this random Bi is there, this will be changed, correct? So your Ci depends on this Bi also. This is random, so that's why it is called semantic secure. This crypto system is semantic secure, because if given two ciphertext you won't and the message, you won't able to guess. Okay, now let us see decryption. Decryption is very easy. For each C, I'm having, for the decryption I'll be getting this C. For each I, just try to check whether it is quadratic residue or not. Okay, for each I, you know the prime factorization P and Q, because that is your secret key. Using prime factorization P and Q, check whether Ci is quadratic residue modulo n or not. If yes, then Mi is 0. Otherwise, Mi is 1. Done? Okay. This was the encryption decryption. Now let us again check. Suppose I am having two messages, M1 and M2. As I told you, what is my C1? It will be some, actually here it will be all in terms of your, so I am talking about M1 is a bit. Suppose I am talking about first bit, because everything is whatever I am going to do here, the same thing will happen on the next next number and so on. So this guy is not dependent on this, and so everywhere, so I can choose anywhere. So suppose I am taking this C1 and another value C2 M2. There are two messages M1 and M2. Let us check the encryption first. Say the encryption will be I'll write B1 raised to 2 and then E raised to M1, and for the next C2 will be say B2 raised to, this B2 is random, B1 and B2 are random, and this E raised to M2, and everything is modulo n. Now let us see addition, whether addition works or not. C1 plus C2. What do you observe? This is B1 square E raised to M1 plus B2 square E raised to M2. These BIs are not same. If you take E raised to M1, this is E raised to M1, this is E raised to M2. This is not equal to some B into E raised to something. Do you agree? This is not same. That means addition does not work here. What about multiplication? Now check. Suppose I am multiplying C1 into C2, then it is B1 square E raised to M1 multiplied by B2 square E raised to M2. What do you observe? I can write it as B1 into B2 the whole square and E raised to M1 plus M2 modulo n. That means this B1 B2 can be say B square E raised to M1 plus M2. Do you see? I got the encryption of M1 plus M2. I was having encryption of M1. I was having encryption of M2. Just by multiplying the ciphertext, I got the encryption of M1 plus M2. Is that clear? So this is again an example of partial homomorphic encryption where it can perform only addition of two ciphertext. Sorry, addition function. Okay. Whereas in the case of RSA, it was only multiplication. If you observe, in the case of RSA, I have already told you, it was multiplication of two messages. Okay. So in the next class, I'll again cover two more crypto system, that is Algorithmic crypto system and BGN. Okay. Thank you so much, guys. We'll see you in the next class.